and the hidden layer neurons do the data processing. Graphical processing units, also called as GPUs and computations. So free GPUs, Google Colab only gives you for Python and Kaggle. In Kaggle, you will get Python. So if you want to use GPUs for R, you have to use Kaggle only. But for Python, you can use both Kaggle, Google Colab, and Kaggle. So if you go to Edit, Notebook Settings, Hardware Accelerator, you can see the notebook settings here, GPU and TPU. GPU is the graphical processing unit, TPU is tensor processing unit. GPU is the graphical processing unit, TPU is the tensor processing unit. So to access or activate it, go to Edit, Notebook Settings, Edit, Notebook Settings, Hardware Accelerator, click on GPU. Make sure you are doing this change right now. Hardware Accelerator for GPU. Graphical processing units and tensor processing units. Now, if you are looking at what is this tensor, tensor is a data type created by Google developers, faster process of images. So if you are looking at what this tensor is all about, tensor is a very advanced data structure. So simply saying, you can see here tensor, scalar, vector, matrix, and tensor. So tensor is a very, very large data structure, as you can see here. Matrix is a 2 by 2 matrix. Tensor can be n-dimensional. Here we can see a 3 by 3 matrix, but tensor can be an n-dimensional matrix. So multi-dimensional object, scalar, vector, matrix, and n-dimensional tensor. So tensor is the data structure which is used. So the libraries are TensorFlow. So the data structure which we are going to use in the library which we are going to use, which is widely used for dealing with large-scale images. Got it, guys, all of you? Okay. Now we will import our other libraries as np matplotlib.pyplot as plt percentage matplotlib inline. All right. All of you have imported the data sets. All of you imported the libraries, guys. And also you have changed the notebook settings. Edit notebook settings. Change the hardware accelerator to GPU. Dot data sets x underscore train, comma y underscore train, comma x underscore test, comma y underscore test is equal to MNIST dot load underscore data. So MNIST is an institute in USA that provided this image data. X underscore train dot shape x underscore. So in train data, we have 60,000 images of 28 by 28. 28 height and 28 width. And in test data, we have 10,000 images of 28 by 28. All right, all of you got the data?
Yes, sir.
They are predetermined scanned images. When you are scanning, you can choose your height and weight. So it has been chosen as 28 by 28 because there are many images. plt.im show x underscore train square bracket 0. So you can see the images are from 0 to 9. 60,000 images are there of 28 by 28 of handwritten digits. So the first image is digit of 5. Okay, can we move forward?
Yes, sir.
For I in range 0, 25, plt dot 5, 5, I plus 1 dot im show, image show, x underscore train, square bracket I, plt dot x takes, plt dot y takes, plt dot grid, plt dot source is outside the loop. So we are seeing the first 25 images of our data. These are the first 25 images of your data. All the digits 0 to 9. Got it, guys, all of you? So these are the 25 images, first 25, 0 to 9. All the images 0, 1, 2, 3, 4, 5, 6. Handwritten images scanned with 28 by 28. Because there are 60,000 images. So in image pre-processing, image processing, pre-processing of images, the most critical task. The first one is we have to reshape or convert. Pixels is the numeric format of image 0 to 255. So the first step is to convert the images into numbers or pixels. Numbers or pixels, because like I told you, algorithms will take only numbers. We have to convert the images into numbers. X underscore train is equal to x underscore train dot reshape, open bracket, -1, 784. Similarly, x underscore test is equal to x underscore test dot reshape -1, 784. Now you might ask, what is -1? -1, one shape dimension. So we are converting images from 2 dimension to 1 dimension, and 28 into 28 is equal to 784. So that is what the numbers mean. -1 represents 1D because images are 2 dimensional. We have height and width. So we are converting it into, and 28 by 28 is the height and width multiplication is 784. X underscore train square bracket 0. This is the data of the first image. So when I printed X underscore train 0, initially I got, when I print after reshaping the data, I get numbers. The next step in pre-processing of images, normalization or min-max scaling must be done all values in the range of 0 to 1, positive values. Because in image processing, we don't want negative values, so we only want positive values. Min-max scalar is the preferred scalar here. X minus X min divided by X max minus X min. So normalization must be done for faster computational process. So X underscore train is equal to X underscore train divided by 255. X underscore test is equal to X underscore test divided by, because min is 0. If you want, you can also check it. X underscore train, X underscore dot max. Oh, sorry, I forgot the brackets. Now it is 0 and 1 because we have divided by 255. So let me do the reshaping. Let me just run it one more time. Sorry. See, min is 0, max is 255. Now, once you convert it, min will become 0, max will be 1. So the same data, which was earlier coming as 255, 251, 160. Now you can see it is all between zeros and, got it guys, all of you? All right. So to build a neural network model, using TensorFlow and Keras, we need certain functions. Immaticus learning. Immaticus learning అని పడుతుంది. అడ్మినిస్ట్రేటివ్ స్టాఫ్ కాలేజ్ అని పడుతుంది. ఉన్నాయి 2-3. నేను మీకు చేస్తాను, వాట్సాప్ చేస్తాను చూడండి. So there are some predefined functions which you need to be used for building a neural network model. The first one is sequential. This is the model definition function because neural networks are sequential linear models. The second function is dense, to define a hidden layer, activation function. And in the first layer, hidden layer, the input shape of the input data, activation functions are linear. The next, dropout, to drop least, which will reduce the size. Then the final layer definition is based on the model being built. So if you are using the activation function to be used is linear. If you are using a classification model, particularly binary, the activation to be used is, so in the final layer activation function, classification, multinomial, the activation function to be used. So number of neurons equal to independent variable. So the definition of the final layer is very important here, which we used using dense function only. The activation function is dependent on the problem statement or the model you are going to build. And you also need to define the number of neurons. For linear, it is only 1. For sigmoid 2, in softmax, the number of neurons will depend equal to the number of levels in the dependent variable. Then we need to compile the model metrics. First, we need to define the optimizer, Adam, which is the default, or SGD, stochastic gradient. We also have to define a loss function, cross entropy, categorical cross entropy for multinomial. And we also need to define the metrics, which is for classification, accuracy, or the F1 score, and for regression, RMSE or R squared. So after defining the model, the layers and all, we also need to compile the model metrics. You have to define the optimizer, you have to define the loss function, also have to define the, so these are the important which you need to define a neural network model using TensorFlow and Keras. Already undamma dantlone ledu March varaku untadi kada. All right guys, all of you got this? Any doubt? Yeah. Now let us start building our neural network model. Keras dot layers. Model is equal to sequential. Model dot add. I'm adding the first hidden layer. 128 neurons. Activation is equal to ReLU. Input shape. Shape is equal to 784, comma. This is the first input layer. Oh, sorry, 1024. 1024 neurons. Model dot add 128 activation is equal to ReLU. Model dot add final layer dense. We are predicting 10 classes. So neurons is 10. Activation is equal to softmax. Because we are doing multinomial prediction, we have to use activation is equal to model dot compile. Compiling the optimizer. Optimizer is equal to Adam is equal to categorical underscore cross entropy is equal to matrix is accuracy. Model dot, oh, what happened? I got an error. Spelling mistake. ReLU.
Categorical, sir. Categorical spelling mistake.
I don't know. Categorical. So we got a model with 9,36,330 weights. The classroom calculation which I showed is only 9 weights. Here we got 9,36,000. All right, guys, all of you got the model. Now we have to label and code the dependent variable. Y underscore train is equal to TensorFlow dot keras dot to underscore categorical y underscore train, comma 10 classes. Y underscore test is equal to y underscore test, comma 10 classes or 10 levels. Now we'll fit the model. Model dot fit x underscore train, comma y underscore train, comma epochs. Epochs is equal to 10, comma batch size is equal to 128, comma validation underscore data is equal to x underscore test, comma y underscore test. Got it, guys? All of you have done it. You didn't convert it into reshape. Input shape you have not given, right? Reshape and input shape, there is a problem. Correct the data shapes. Rest of you guys got the output. So the model is 99% on train, on test 98.16. All right, guys, all of you got this. So similarly, we can run a model. There is one more data set, fashion MNIST, x underscore train, comma y underscore train, x underscore test, comma y underscore test is equal to fashion MNIST dot load underscore data. Fashion MNIST x underscore train underscore test dot shape. This is also a data of 60,000 images, 28 by 28, but of images related to, all right, all of you imported the data. You can copy the code from top, that for loop for seeing the 25 images, paste it down. So these are the images we have. All right, all of you got this. Now we need to follow the same process. First, we need to reshape the data or convert data into pixels. So x underscore train is equal to x underscore train dot -1, comma 784. X underscore test is equal to x underscore test dot reshape -1, comma 784. Then we data using x underscore train is equal to x underscore train divided by 255. X underscore test is equal to x underscore test divided by 255. Now we will build the neural network model. అవును salary and పడట్లేదు కదా, ఇది ఇమాటికస్ లెర్నింగ్. ఓకే, అది వేరు కదమ్మా, ఇమాటికస్ లెర్నింగ్ అని పడదు కదా. ఇమాటికస్ లెర్నింగ్ పడ్డదా, వేరేది పడ్డదా? All of you have built the model. So this is a model with 9,85,000 weights. And the same process, label and code dependent variable. Y underscore train is equal to TensorFlow dot keras dot utils dot to underscore categorical y underscore train y underscore test is equal to dot keras dot utils y underscore test. Again, here we are predicting 10 categories. Model dot fit x underscore train, comma y underscore train, comma epochs is equal to 10 is equal to 128. Validation underscore data is equal to x underscore test, comma y underscore. So if you look at this model, we got 91.30 train and 87.78 test accuracy. 91.30 train, 87.78 Right now I don't have. I'm out of station. Call me later. So complex images where accuracy tends to be lower. These CNN models, there are different variants like VGGNet, etc., which are very complex. Now, if you are looking at a basic CNN model, convolutional layers, and finally network layer. So a typical convolution neural network will have initially convolution layers followed by the pooling layers. Then you will have the neural network layer for predicting the. So this is the basic CNN model developed initially. So this is a typical convolution layer neural network. You have two convolution layers, then the pooling layers, then flattening it into a single output, and then fully connected layer, which is the neural network. And finally, softmax prediction layer. All right, all of you got it? So the first layer is very important, the convolution layer. The convolution layers are very, very critical. The convolution layers will apply a filter so that it reduces the dimensionality of the. So convolution layer is the first layer which will focus on reducing the dimensionality of the image by applying a filter. The convolutional layer is the first layer which reduces the image dimensionality by applying a kernel filter, 2 by 2 kernel, 3 by 3 kernel, that helps in reducing blurriness, sharpening images, size of the image without losing any information. So here you can see the calculation. This is the actual image data, 1100, and we applied a 3 by 3 kernel, unit matrix, 3 by 3 unit matrix with stride 1, 3 by 3 kernel filter with stride 1. Stride 1 means 1 cell it moves. It moved from 1 to here. Now it is kind of calculating the last. So doing the multiplication of rows with columns. So if you do the row with column, you will get a smaller matrix. So 1, 2, 3, 4, 5, 6. So this is a 6 by 6. By putting 3 by 3, you got 3 by 3 image. Convoluted feature of 3 by 3. So we have effectively reduced the image size. This is the job of convolution layer. This is the job of convolution layer.
Yes, sir.
Now, another important thing you need to understand within the convolution layer is adding a layer of zeros on the outer end of the image for efficient and to prevent information. So padding is also one of the interesting thing which happens in convolution layer. So padding is equal to same. You can see a outer layer of zeros are added. So outer layer of zeros will be added to make sure the edges are detected properly. Now, after convolution layer with padding and all, the next layer is the pooling layer applies a on convolution layer for reducing image dimension. Two types of pooling are there. Average pooling. So pooling layer is the layer which we generally apply after the convolution layer so that you can reduce the image. So this is the concept of pooling. Max of each quadrant is max pooling. Average of the quadrant is average pooling. Maximum value in each quadrant is max pooling. Average of all 4 values in the quadrant, we call it as average pooling. So max pooling and average pooling is used to reduce the image dimension further. All right, all of you got this? Pooling. Flatten layer must be done is process of into a single array, which will be input for. So this is what flatten will do. Pooling, you will get a matrix like this, which will be converted into a single, just reshaping the matrix to a single vector or a single array. So flatten is the one which is to be implemented after pooling. Now, finally, has to be defined. Final, the neural network optimizer, loss function, and matrix. So finally, we have to build a neural network using the sequential activation and final layer definition based on the model we're building. So these are the steps involved in building a convolution neural network. So convolution neural network will have initial convolution layers, followed by the pooling layer, followed by the flattening layer, and then the neural networks layer. So before the neural networks start, a lot of these convolution layers are there which work on images. They work on reducing the dimensionalities, reducing the size, improving the image data, augmenting the image data and all, so that the model can read and work better. So that is the job of convolution layers. Once convolutions, pooling all are done, flattening is also done. Finally, we will build the neural network. So this is the CNN theory. Let us build a CNN model. Import NumPy as NP, import matplotlib, pyplot as PLT, percentage matplot keras dot datasets fashion underscore. So the same fashion MNIST on which we built a normal neural network model, we got 91 train accuracy and test accuracy of 87. So let us see whether the accuracy improves if we build a CNN model. X underscore train, comma, X underscore test, comma, Y underscore test, underscore MNIST, dot load underscore data. Same fashion images data. Let me see if I have activated notebook settings. No. All of you activate the GPU also. You have to run all the time. Okay. So I'll terminate the whole session. So please activate the GPU, edit notebook settings and GPU. Once you have imported the data, please confirm. All right. Shall we move forward? So again, we have to do the same thing. Reshape the data, convert it into numbers. X underscore train is equal to X underscore train dot reshape X underscore train dot shape square bracket 0, comma 28, comma 28, comma 1. X underscore test is equal to X underscore test dot reshape X underscore test dot shape square bracket 0, comma 28, comma 28, comma 1. X underscore train is equal to X underscore train float 32. So from float 64, we are reducing it to float. X underscore test is equal to X underscore test dot as type from 64 bit to 32 bit. Then we need to normalize using the min-max scaler. X underscore train is equal to X underscore train divided by 255. X underscore test is equal to X underscore test divided by 255. Then we will label and code the dependent variable. Y underscore train is equal to keras dot utils dot to underscore categorical Y underscore train, comma 10. Y underscore test is equal to TensorFlow dot keras dot to underscore categorical underscore test, comma 10. All right, can we move forward? So let us import the functions. Keras dot models from keras dot layers normalization from keras dot layers. CNN is equal to, now we are adding the first layer, convolution layer, CNN AD dot add convolution 2D, open bracket, kernel size is 3, 3, activation is equal to, comma, input underscore shape is equal to 28, 28, 1, comma, padding also we are doing, padding is equal to same. So the first convolution layer, 32 filters, 3 by 3 kernel, activation is ReLU, input shape is 28, 28, 1, padding is equal to same. The first input layer which we have defined. Then CNN dot add batch normalization, because we are passing the images in batches, so it will normalize according to the batch. Then we will add one more convolution layer and copy the same from the top. Just remove the input shape because we don't need the input shape. Second convolution layer, 32 filter, 3 by 3 kernel, ReLU activation, padding is equal to, again, third convolution layer, this time 24 filter, 3 by 3 activation is equal to ReLU and padding is equal to same. One more convolution layer, this time 64 filter, activation, ReLU, pooling is equal to same. Then 32 filter, 3 by 3, activation is equal to ReLU, padding is equal to same. So basically, I have added 1, 2, 3, 4, 5 convolution layers. So 5 convolution layers. Then we are adding the pooling layer. Pool underscore size is equal to 2 by 2 pool size. CNN dot flattening layer to flatten the output to a single vector. CNN dot add the first layer of your neural network, 128 neurons. Activation is equal to ReLU. Then the final output layer, CNN dot add, we are predicting 10 classes. CNN dot compile, optimizer is equal to Adam. Loss is equal to categorical underscore cross entropy, comma, metrics is equal to. So we built a model with 8,53,218 weights. All right, all of you got this? Now we'll fit CNN dot fit X underscore train, comma, Y underscore train, comma, epochs is equal to 20, underscore size is equal to 128, validation underscore data, X underscore test, comma, Y underscore test. Improvement in the model. True is not subscripted. So forgot to give the name to the model. CNN model is equal to CNN.fit. Oh, forgot the legend. URT.legend. So you can see the train and test accuracies. All right, all of you got this? So this is a convolution neural network model which we have built on the same Fashion and IST, where our train and val accuracies were less than 90% there. Here we got above 93% or close to 93% is what we're getting. So comparatively better performance than the basic neural network model. So this is a convolution layer network model with 5 convolution layers. 1, 2, 3, 4, and 5 convolution layers we have added for working on the images with different filter sizes, but common kernel and common activation function. PF underscore flowers is not working. So it is from PF underscore flowers. You can work on this data. Okay. Any doubts, guys? So all of you are able to run the model.